So in this lecture, we'll take a look at the energy and hydraulic grade lines. The energy and hydraulic grade lines represent a graphical approach to solving these problems. So first, if we rewrite Bernoulli's equation in the following form, then each of the terms has a length measurement. So we define what's known as the h's to be the sum of these three terms. This first term is known as the velocity head. Then we have the pressure head and elevation head. These two terms together are what's referred to as the hydraulic head. So the velocity head plus the hydraulic head is going to equal the total head. So the important points when forming these energy grade lines is as follows. First, the Bernoulli equation can be expressed in terms of the total head of the fluid. A plot of the total head along a pipe or channel is what's known as the energy grade line, or EGL. Provided there are no pumps or turbines and friction losses are not considered, then this line will always be horizontal, as shown in the top figure. The energy grade line is going to be constant, unless there's pumps or friction or turbines involved. The hydraulic grade line is a plot of the hydraulic head along the pipe. So if the energy grade line is known, and then the hydraulic grade line will always be V squared over 2G below the energy grade line. So again, the total head is equal to the velocity head plus the hydraulic head. The energy grade line is simply the sum of those two terms. Velocity head plus pressure hydraulic head, so that's going to be constant. The HGL is going to be just these two terms here added together, which will always be less than the energy grade line by this velocity head term. So let's take a look at example 5.7. So here we have water flowing through a 2-inch diameter pipe at 0.2 cubic feet per second. If the pressure at point A is 30 psi, determine the pressure at C and draw the energy hydraulic grade lines from A to D. Neglect friction losses and take gamma to be 62.4 pounds per cubic feet. So first we can calculate the average velocity to flow to the pipe. Q is V times A. So we know what Q is. We're given that. We know what the diameter of the pipe is, so we can calculate what the velocity. So since this pipe has a constant diameter over its length, this velocity has to remain the same according to the continuity equation. So now let's apply Bernoulli's equations to point B and C. So we can write both sides of the equation. The energy at point B has to equal the energy at point C. And we can plug in the information that's given. We know what the gamma is. We know what the pressure is at A. We know what the velocity is. Since we'll take our reference level to be at B, so this Z term is going to be 0. The only thing we don't know is the pressure at C. So we can solve this equation. Notice here also that you have to be careful with this Z term at C, because it's not, you have to calculate what the horizontal distance is, right? So it's 4 feet this way, so it's 4 feet times the sine of 30 is going to tell you the height from the reference level to C. So if you plug those terms in, you get 29.1 psi to be the pressure at C, which is also going to be the pressure at D, because again, the continuity equation. The total head remains constant, so we can actually calculate that. We can choose any point we want. Let's choose point B here. We can plug in our information that's given and calculate the total head H to be 70.5 feet. So we can also calculate the energy grade line at B. So again, it's PB over gamma plus ZB, so we can plug in those terms. ZB is 0, again, because B is at the same as our reference level. Similarly, we can calculate the energy grade line at C. So we can plug in the terms we know for the pressure It's BC divided by gamma. ZC again is 4 feet times the sine of 30. So we calculate that to be 69.2 feet, exactly the same, and that makes sense because the pipe is a constant diameter. The velocity of the pipe is constant, so the velocity head is always going to be equal to the v squared over 2g, 1.30 feet. So finally, we can form a plot of the head versus the distance along the pipe. So starting at A, we calculated both the EGL and HGL, and you notice the EGL and HDL stay constant all the way through the pipe because essentially the diameter doesn't change. The only thing we have is that the difference between these two is simply the velocity head, which we calculated to be 1.30 feet. So let's take a look at example 5.8. Here we have water flowing out of a large tank through a pipe system. Notice here the pipes have different diameters. B to C is a different diameter than C to D to E. Again, we want to draw the energy and hydraulic lines for the grade lines for the pipe if friction losses are neglected. Here we assume that the water level in the tank remains essentially constant. We assume it's a big tank, and so that the V of A is approximately 0. It's also at atmospheric pressure, so that's approximately 0. Atmospheric pressure here, atmospheric pressure out here. So again, it's the same at A and E. So this term and this term is essentially going to be 0, and all we're left with is the height Z of A, which we're told is 4 meters plus 5 meters is 9 meters. So we start up here with the EGL. It's the green value. It's 9 meters. Now the EGL also remains at this level since there are no energy losses due to friction in the pipe. So the green line can extend all the way across from A all the way to E. Now let's work on the hydraulic grade line. We found what the energy grade line is. It's 9 meters. So in order to find the HGL, we need to find the velocity at each of the point. So first of all, let's find the velocity at E. So the velocity at E, we can use Bernoulli's equation for that. We know the information at A. We know the information at E. So we can plug that value in. So P of A is 0, V at A is 0, Z of A is 9 meters. P at E, again atmospheric, is 0. Z at E is 0 because that's at our reference level. The only thing we don't know is V at E, so we can solve for that. It's 13.29 meters per second. Now, to find the velocity at B, we're going to use the continuity equation. So again, we're going to write our familiar continuity equation, and this line looks familiar to us. We know what V of E is now. We know what the area at E, because we know the diameters of the pipes at A and at B. So we can calculate the velocity at B, 3.322 meters per second. So finally, we can calculate what the hydraulic grade line is because it's VB squared over 2G. So it's at B, it is 0.5625 meters. So here you see it at the energy grade line stays constant, the green line, but once it gets to B, it drops down. How far does it drop down? It drops down 0.562 meters. So that's the blue line you see. So the green line is the energy grade line. The blue line is the hydraulic grade line. So the hydraulic line is going to change. So it stays constant through here because again it's a constant diameter pipe. So the tracks along without changing until you get to C, because at C the velocity changes. And again, the velocity is the same here as it is there. We calculate what VE squared over 2G is. It's 9 meters. So here you'll see it fall down by 9 meters. The energy grade line falls down by 9 meters from the EGL. All right, so that's the end of this particular lecture. I'll see you in the next lecture.